So if you so here's then the extra video where we need to do duals. So that's then number 3. So on vector space, V star is then the dual, and that's the collection of all linear maps from the vector space to K, depending on your order, where A is linear. So the dual, which we denote by V star, consists of all such linear maps going from your vector space into your group. Now into whatever field you have, real or complex. If L going from V to V is a linear map, then we define the transpose L apply to A as the map that precomposes with L, and then you apply your A. So then you get first a map going from V to V, and then you apply your alpha to map into R, and that in total will be a linear map from V to R. And the reason why it's denoted as the transposed is that if you pick any sort of basis of the vector space and write L as a matrix in this vector space, then and then you use the same basis to write alpha as a vector, then this action will then correspond to L will then work as the transpose matrix. We remark that if I have L and K going from V to V, then L, just as with the normal transposed, LK transposed is equal to K transposed L transpose. So it changes the order just in the same way. And then we define representations for the representations of Lie groups. If V large pi is a representation of G, then V star pi star is defined as pi star of A alpha equal to taking A inverse, and then the transposed. And why do we need to take A inverse? Well, you can test out the problem, what happens if you don't take A inverse, that you actually then don't get a group homomorphism. But it's related to the following thing here. So this is sort of an anti-homomorphism in the sense that it reverses the order, takes left to right. So you need another that sort of take things that takes left to right. And this, in order for this to actually end up being a group homomorphism, and that is here by taking the inverse. So if you want to act on the dual, then you need to act by the inverse, not with the element itself. So A in G, alpha in V star. And then if you differentiate this, you get the following conclusion. So if V pi is a representation of G, then V star pi small pi star is defined by pi star x of alpha equal to minus pi x transposed applied to alpha. Where x is in the Lie algebra and then alpha is in the dual. So, and this minus is then in order for the such that if we keep the property that if these are associated, then the corresponding dual representations will also be associated, because you're going to differentiate something in here to get this representation here. And it will be your exercise this week to show that this this does indeed hold for this case. Yeah, and then one more thing, you can of course then combine them. So if you want a mapping from a vector space to another vector space, for example, you can do that by combining the tensor product and duals, which is also one of your exercises to show. Okay, that's it.